All right, welcome back, everybody, to the Additive Snack podcast. I'm your host, Fabian Alefeld, and today we have another really awesome episode around a topic that we have not discussed so far, which is the whole industry of tool and die. And therefore, we are super excited to have Vilas Ravindra with us today. Vilas leads the Additive Manufacturing Group at AarKel, Tool and Die. They're a company based in Canada, and they really are at the forefront of innovation when it comes to integrating additive manufacturing into the tooling industry. They have been a key contributor to various innovations in that space, and therefore I'm super excited to talk to Vilas today about a few pieces of their journey into additive manufacturing. So we'll talk about how additive manufacturing has been integrated into their operations. We'll talk about the die casting process, the injection molding process. We'll also talk about a few case studies and parts that Vilas brought with them to kind of emphasize the impact that additive manufacturing has on the tool and die industry. So without any further delay, Vilas, welcome to Additive Snack.
Thanks, Fabian. Great to be here, and thanks for hosting.
Sure, man. Excited to also learn more about the die casting and injection molding process from my end. I'm more proficient in the additive manufacturing space, but not in those spaces. So I'm sure I'll learn a lot as well. But before we dive deeper into that, let's talk a bit about your background. How did you get involved in additive manufacturing?
Yeah, I mean, it's. I've always been inclined to the science and innovation ever since I was a kid. I've always been wanting to be part of the automotive industry. I loved cars growing up as a kid, so naturally I was inclined to go with mechanical engineering. Um, and I remember during my undergraduate, I had been part of this club called Formula Student Racing, which was organized by SAE, Society of Automotive Engineers. And the buzz of 3D printing was very strong, even back in 2010, 2012. And I remember taking a 2-week course of rapid prototyping, and it was a PLA filament printer doing some small 3D printed parts. It was very exciting to see this technology. And that's kind of where I picked up on this and completed my bachelor's and came to North America, did my master's in automotive engineering at University of Windsor. And when I get the opportunity to be part of AarKel Tool and Die and integrating additive into the tooling world, it was a great opportunity, and I picked up on it. And fast forward 5, 6 years, here we are.
Super cool. Yeah, I think additive, it's interesting that you say that, has had very early implementation successes in the Formula students teams, probably before Formula One even, which is quite interesting. And I would say, get a lot of requests from Formula student teams. Unfortunately, we cannot support everyone out there, but it is interesting how quickly those teams have adopted additive manufacturing.
Exactly.
Um, so what about AarKel? How did maybe tell us even about the history of AarKel a little bit, and touch on how additive manufacturing started to become implemented. As far as I understand, AarKel is not a additive company from a historical perspective, right? But at some point, additive became a viable technology. How did that happen?
Yeah, I mean, so AarKel Tool and Die is a global leader in tool and die manufacturing. It's a pretty old company, formed in 1977.
Hmm.
And they've been specializing in plastic injection molds and also die casting applications. So that's kind of where the specialization lies. They're also into automotive lighting and trim dies, and they have a global footprint. So we have offices located in India, we have facilities in Mexico, in Alabama, and we're predominantly spread out well over Canada. We have about 4 to 5 facilities. So right from design, feasibility, manufacturing of the die, and even sampling, we do it all. So we're a one-stop solution for our customers. So that's kind of what we specialize in. Um,
Mm-hmm.
5, 6 years ago, we were hearing a lot about metal 3D printing. That's the first time when I was introduced to metal 3D printing. And EOS was a huge driver in that. And when we heard about this technology and the industrialization side of it, it kind of poked our interest. And AarKel has always been at the forefront of adopting unique technologies and trying to innovate in every aspect possible. So it was this is part of that vision of being at the forefront of innovation. So we saw the additive market and the way we could utilize it in molding applications and provide unique solutions to our customers. And that's how we got involved with the additive space.
Interesting. So it was really a continuous search for new technologies and additive came around the corner, and you guys started to look into that. So how did that first implementation then look like? A lot of companies struggle with that, right? How do you find that first application? How do you prove it out? How do your customers perceive it and assess that risk? What did that process look like?
So in the beginning, like it's important to understand that even 5, 6, 7 years ago, even though EOS introduced the M290, the M280 was the first kind of version and it came out. It wasn't really built for molding or tooling applications. It was a very generic machine which could be utilized in various platforms and applications. So part of the challenge was to figure out how we could use this machine and print stuff on it which can fit in a pre-existing mature process. So that was kind of really a challenge for us, because when you look at the developments we've done, like hybridization, a lot of these unique proprietary techniques we've developed, it takes quite a bit, because you have to figure out the fixturing, how are you going to machine it, how is the stock allowance, how are you going to heat treat it. So there was a lot of playing parts in this, and I think those were the kind of initial challenges we saw of it. And the technology is quite new and it's growing. So the second part of the challenge was the learning curve. So because it's not a plug and play device, essentially, there's a lot going on in the process. So you have to understand the printing parameters. You got to understand the part quality. You got to understand the mechanical properties of the material. So there was quite a learning curve, and that's still the case. So at AarKel, we always believe we're forever learners. And every single day, every project, every unique customer we work with, it's a new problem, it's a new solution, and we're constantly learning. So that's kind of what we figured out very early in the development of additive with AarKel.
Yeah, very interesting. I mean, the learning curve is always a bit underestimated, I think.
Exactly.
It's treated as just another manufacturing technology, but I think if you compare it with the learning curve of a CNC machinist, that's I think is taken a bit more seriously, just because companies have the experience and understand how complex it is to program a mill for a certain application. On additive, we have even increased complexity, right? From orientation to support structures to process and parameter optimization, which definitely takes a good chunk of time to get familiar with all of these parameters. So you guys realized that probably the hard way by try and error and so on.
Yes, absolutely. We made a ton of beautiful mistakes. Costed us a little bit, but you learned the hard way. And I remember even initial days when we were doing hybrid, it was a very unique thing that we didn't think about, but it was very obvious. We were putting these blocks of steel on the CNC machine, and they have these magnets. They have these electromagnets where the hybrid base sits on these electromagnets, and you CNC machine the base, and then you print on top of it for reducing cost. So you don't need to, we only print the essential part. And when we magnetize the part, we put it in the printer. When the powder was recoating, you could see that polarity. You could see now the powder's basically going towards the magnetic poles, and you couldn't even coat it properly. So these are all very unique learnings, because the powder has a very strong magnetic property and it aligns with those poles. So, we realized, oh, you can't even use magnets on these. So simple mistakes like that. It was a very nice and adventurous learning curve for AarKel.
Yeah.
But right from the small, stupid mistakes to really good ones, and we learn a lot from it.
Interesting. I was actually not aware of that. So you just had to not use magnets in
Yeah,
the machining process.
exactly. Yes.
Okay. Let's dive a bit deeper into the two main fields of applications that you guys work in. I mean, one is of course die casting, mainly inserts, as far as I understand, and the other one is injection molding. Let's start with die casting. If you could even maybe take us through the die casting process chain. How do I get from molten material to a final casted part? And then we'll dive a bit into where additive manufacturing plays a role in some of those sub applications.
Sure, sure. I like to explain it in a very simple way to non-automotive, non-tool and die listeners. Is that it's just basically making, like, take an ice cube or ice cube tray and you pour molten chocolate into it, and you freeze it, and after some times you get all these beautiful chocolate cubes. And it's the same thing, but essentially imagine it in a production environment where you're making thousands and thousands of chocolate cubes, but then the solidifying of those cubes takes time. So imagine if you're pouring molten um, uh, chocolate into these ice trays, and it takes 1 minute to cool. Now the manufacturer is thinking, how can I cool this tray in 10 seconds so that I can produce more
Mm.
chocolate? So that's kind of the idea. Instead of making chocolate, we're making automotive parts, whether it is transmission housings or shock tower components, or whether it's the water jackets or anything. We make the molds for those, and those parts are essentially cooling, and they're casted components, and they take time to cool, which creates the cycle time. So if we're making a part, it takes 100 seconds to solidify and cool. Now we are looking at ways on how can we use additive manufacturing to cool certain areas which take longer to solidify, and we can improve the cycle time so that we can save those crucial seconds. In the beginning, it might not seem like a lot. It may be a few, 2, 3, 4, 5 seconds. But then at the grand scale, when you look at an entire shift where you're making 5,000, 6,000 parts, now it becomes significant.
Yeah. Interesting. So really the main driver is cycle time. And yeah, out of 100 seconds, 3 seconds, I mean, that's 3%. That's not a percentage that you can just underestimate. Which parts of the die casting process today are now being additively manufactured?
Well, it's not a straightforward answer, but basically anywhere where we're able to make a small insert out of it. So high wearing component where we see a lot of hot spots in the die. If we're seeing porosity areas where we have to improve porosity or push away porosity to a non-critical region in the die, or even if you have to thermally regulate the die, or it's taking, or for cycle time improvements, like I explained before, there are different reasons why we'd adopt 3D printing, but the part sizes
Mm-hmm.
can vary anywhere from a small sub-insert, which is 5-inch cube, to a short block, which is the first part which interacts with the aluminum to cool down the biscuit region. It takes anywhere from 11 to 12-inch by 4-inch parts to 5-inch cube parts. It's completely dynamic and it's completely case by case, but you can basically insert a small part in the mold with 3D printing, and you can cut out that region, and we can just isolate that region and just 3D print that portion wherever there's a problematic area. So it's applied in all sorts of design and different scenarios.
Okay, so in my ice cube tray, I have an inserts for a certain feature in my final application, and these inserts tend to create challenges via hotspot regions or excessive wear. I think you even brought a cut open insert with you, right? So could
Exactly.
you for that.
Sure, sure, absolutely. So I have a part for here. So this is a sub insert. So as you can
Awesome.
see, if I show, that's the cavity region. So imagine that this portion is just a small piece of the big mold. So imagine your engine cover or a transmission cover. So these are all the ports of that, but then that's an area where thick masses are forming. And so it takes time to solidify. So, traditionally, we're just waiting for that casting to cool down. But in this case, because of the power of additive manufacturing, what we can do is we can insert this area in the mold and we create a sub insert, and you can bring cooling really close to the surface of the die. And now essentially you
Mhm.
can see that this conformal cooling channel is conforming to the cavity surfaces. And we're able to extract a lot of thermal energy out of this region in the die. So the beauty is that the complexity of the conformal cooling line can be extremely high or can be extremely basic. So the flexibility is there with AM, and you can bring it super close to the surfaces or you can bring it away from the surfaces. So the sky's the limit in terms of design. The advantage of AM is that you can introduce such kind of intricate cooling structures and geometry, and you can thermally regulate particular region or problematic area in the die.
Okay. And what role? How much of that is now experience by experienced tool designers, where they understand the process and the complexity of it, and they can already tell that there will be certain hotspots in a certain area. So we'll pivot to additive manufacturing for certain inserts versus, I'm guessing typically these channels are just drilled by a straight line. Is that more of an experience-based design process, or does simulation and software play a huge role there as well?
Yeah, so I mean, it's kind of both. So, when you look back 15, 20 years ago, it was all based on experience. So it's naturally a combination of the two. When we're looking at the die and we look at the part and okay, we see, okay, these are all the areas where you might expect some issues. You might expect the thick mass sections, you might expect some solidification issues. And what we've done during the recent past is the last decade or so, we've integrated with Magmasoft, which is another software for more flow simulation. So when it's a new die build or it's an existing tool as well, we run simulation to show exactly where the issues might appear and where the hotspots are, where the porosity is, and where we can improve. So the simulation kind of helps tremendously in identifying which regions are compatible for additive manufacturing. And traditionally, where, like you said, you would drill straight lines and create a circuit for the water line. Now, what we'd do is we'd cut a small pocket or we'd cut an insert out in the mold. And now we would send it to us. The design team would, the diecast design team would send it to us, and we would look at it at a completely different approach and would introduce all sorts of conformal cooling techniques, different multiple circuits, and different iterations, and would feed that thing back into the simulation to see what the potential of
Okay.
additive is. So the simulation shows whether the additive manufactured solution is better or worse than the traditional version. And that's kind of the initial idea of how you can integrate additive into a die.
Okay, so simulation definitely is also an aid in the decision-making process, not
Absolutely.
just in the design
Absolutely.
process.
Yes.
Yeah. Okay. And then, so we talked a lot about now cycle time and overheating. What what is the lifetime of a additively manufactured insert versus a conventionally manufactured? Which, and maybe we even should touch on that. Conventionally, I'm guessing that's raw material, that's machines with drilled cooling channels. Correct me if I'm wrong here. If I'm wrong, please explain us the conventional process, and then how comparable are they from a lifetime perspective?
Yeah. So traditional inserts are much cheaper naturally because it's CNC machined and they have surface coatings on it and they're inserted. But they have lower performance and they have limitations of how much you can cool it and the complexity of the water lines. There's a lot of limitations there. with 3D printing, because this entire industry is rapidly growing, the portfolio of materials also growing. So if you look
Hmm.
at just tool steel, there are 50, probably even 100 plus materials available in the market. And, every supplier, every manufacturer has their own spin. They tweak the chemical composition, and, they have something extra to offer. Maybe your material is extra tough, or some other material is, you don't need to heat treat it. So there's different kind of materials out there. And AarKel uses certain materials which are compatible for our dyes. And what we see is that the materials are so advanced now that in our testing and feedback from our customers, they're actually surpassing the traditional life of an insert. So I remember a particular project we were working on, BMW shock tower. We had introduced a sprue bushing insert over there. And that insert,
Mhm.
the traditional one, had a lot of issues because there was die soldering issues, porosity issues, and cycle time issues. And they were probably frequently changing it, time maintenance, 50, 60,000 shot. And that was the life of the insert. But then when we put this 3D printed insert in, now we were seeing the life being expanded to 100,000 plus shots, and we still had a
Wow.
ton of life in that insert. And many times they're over efficient. So we have to time it. And that comes back to the simulation, where if you leave the water on in the dye continuously 100% of the time, sometimes you're actually converting that hot spot into a cold spot because the 3D printed
Mhm.
insert is over efficient. So now all of a sudden you have to time the insert. So, okay, I'm going to switch on the water for just 15 seconds or 20 seconds until the dye is thermally regulated, and then I'm going to cut the water off. And all those inputs are actually being provided by the software support and the feedback from the customer.
Interesting. So you actually almost improved the performance of cooling, at least too far, where you now have to dial it down a little bit.
Exactly.
But I guess which actually means you kind of hit the limit of cycle time reduction, at least when it comes to that insert, I'm guessing. But you have a 2x lifetime increase. So you also have reduced downtime of the whole process, etc., which should also increase the overall output as well.
Absolutely. So you're doing multiple things here. You're solving the cycle time issues or whatever specific issue that customer had in that area. And not only that, you're improving the life of the entire insert, and you're able to improve the overall process itself because you're introducing additive. So your flexibility is higher. Now you can thermally regulate the die, and you can keep optimizing the design based on the need of the customer.
Interesting. Super cool. Now let's shift gears a little bit. No pun intended here.
Sure.
And talk about injection molding, which is another very interesting piece of the puzzle. I would I would say, from at least from my knowledge, injection molding actually adopted additive manufacturing before die casting. At least as far as I'm aware, those are some of the earliest end-used part applications that I know in the metal additive manufacturing space. Um, and you've mentioned to me before that AarKel is actually, or has been involved in the Hummer EV program, if I'm not mistaken, via a injection molding tool. Could you talk about that project a little bit?
Yeah, just a small correction. The Hummer EV program platform is actually a die casting project that we did.
Oh, it's also die
It's a die
casting.
casting
Okay.
project, yes. So the advantage of these EV programs is that it's a blank slate, right? So it's a
Mm.
very new tool build. So the integration of additive solution is fairly easier compared to existing older platforms because the design is brand new and we're completely designing the whole mold. So very early in the design stages, when we see these issues, we can integrate additive solutions right off the bat. And it
Mhm.
helps with part consolidation, and we can complete the entire development cycle much faster, because you don't need to have 3, 4, 5 tryouts, because naturally what happens without additive is that you go for tryout number one, tryout number two, you discover some issues, then you make engineering changes and you tackle these problems of hotspots, porosity, and cycle time. But then with additives and these EV platforms, you're able to introduce these solutions right off the beginning in the design stage. And now you don't need that much of tryout. You don't need to go and solve the problems later. You're already discovering them early in the design stage. So that's kind of the beauty of additive and these electric vehicle programs, but since you can innovate very early.
Interesting. Interesting. So that really means that the advancements of additive and their impact on die casting, I could imagine also means that there is just more and larger and more advanced die casted applications within the vehicle. Can you talk about that a little bit? Like, where do we see now die casted parts within the newer EV platforms versus maybe the more legacy platforms that we see out there?
Yeah. There's since it still shares a lot of common parts. It's just that the engine's not there, and then you have a new battery housing. So battery
Hmm.
housing is a great opportunity for 3D printing. And if you look at the shock towers or other components in the car where you're using die casting techniques, they still retain in the electric vehicle platform as well. But the newer addition is like on the Hummer EV platform, we're working on the cover case of the electric motor itself. And we also have these battery housings where you can introduce additive manufacturing and solve some of the issues that they might have. So there are a lot of common parts between EVs and internal combustion vehicle. But the big change is that since it's a newer platform, we can get in early and we can introduce these changes.
Okay, interesting, interesting. Okay, let's talk about injection molding because, like I mentioned, I think that is also an application that is not really talked about that much in the additive industry, at least. It's kind of taken for granted, I think. Tell us a little bit about, you know, where does AarKel introduce additive manufacturing when it comes to injection molding tools? What are the benefits, and what's the difference maybe to die casting?
Yeah. So in terms of um, injection molding, there's a little different. It's a completely different animal. We don't deal with uh, the forces and the dynamic loading conditions that we see in die casting, but
Hmm.
on the other side, we deal with different problems as well. So typical problems in plastic injection molding you see as gas. And when you're trying to fill the plastic in the mold, they develop this heat and pressure pocket, and the air does not have anywhere to escape in the mold. And it becomes super hot and it creates all sorts of defects in the plastic component. So with additive, what we're doing is we are again isolating those last to fill regions in the mold, and we are creating engineered porosity, which we call venting. So we basically create uh, small porous slots, which are small enough to make sure the plastic does not flash, but they're big enough to let gas to escape. So this is kind of a unique proprietary process that AarKel has developed, where anywhere in the plastic injection mold you have a gas trap issue, you can introduce venting. So speaker grills is a great place where it's notorious for gas traps. And you can build these very intricate venting around the speaker grill, the mold side, and now you can create parts with more ease. And the other thing to also add to this is that you can combine venting and cooling solutions in plastic injection molding. So now all of a sudden, you have the exact same insert. And when you have deep ribs and areas which are prone to gas traps, you can add venting, and just underneath it, you can add a conformal cooling circuit as well. So now in one insert, you're able to provide two solutions, that is conformal cooling and venting. So that's how we're using additive in the injection molding side.
Super interesting. I mean, porosity typically is such a negative term in manufacturing, but in this case, it is planned porosity by controlling the laser parameters in a way where you introduce porosity exactly at the right spots. I'm guessing even with connected to certain channels that then get the air out of the tool, which is, back to our initial conversation, requires a lot of deep understanding of the additive manufacturing process, and I think is a art by itself, and an
Absolutely.
underutilized aspect of additive manufacturing, right, is to control these parameters down to the finest detail.
Yeah, absolutely. I think even for us, when we were trying to design and develop this unique way, we actually stumbled upon it by a mistake. We were trying to do some design of experiments, and we were trying to print some different densities and things like that, and we discovered that you can create this foam sort of a structure, and it's not 100% dense, but then you can control the level of porosity, and now you can isolate it. And we still use simulations in these as well, right? So the simulation helps us to identify which are the areas in the mold which are going to be last to fill, and we know where the pressure pockets are going to be, and based on that, we are going to design these venting and put engineered porosity in that area, and to help the entire tool breathe much better. And now the molders, and we've since AarKel owns AarKel Injection Technologies in Windsor, which is a sampling and low volume production facility, we have done a lot
Mm-hmm.
of R&D experiments over there, and we see that the molders love the venting, because now you're actually using less tonnage of the machine, and instead of forcing the plastic inside these critical areas, now because of the venting, the tool is breathing much easier, and you can use less tonnage of the machine.
Interesting. So that has also, let's talk about the effects of that. Cycle time, I'm sure, plays again a role. Cooling down the material faster, reducing hotspots. Breathability then has an impact on reduced tonnage, which should also have an impact on energy consumption and just in general the complexity of a setup, I could imagine.
Yeah, when you start using lesser tonnage, it's just easier on the machine, right? Because
Yeah.
now all of
Okay.
a sudden your parting line is going to be wearing much more heavily, and the machines are pushed much harder, right? It's almost like driving your vehicle at 150 kilometers an hour every single day, versus now all of a sudden, like, you've improved the aerodynamics of the vehicle, that you really don't need to push the engine much harder, but you can throttle it at 80% and you can still get the same efficiency. It's kind of the similar
Mhm.
analogy where, you don't need to push the machines too hard anymore. And we call it packing in injection molding. So you don't need to pack the tool too hard, and you can just reduce the tonnage, and you're able to easily fill those regions, and you're not getting a ton of defects because you're venting the gas out of all these regions in the die.
Okay, cool. Which end applications is this interesting for? Do you see in additively manufactured injection molding tools in various different aspects, or does it apply specifically for applications like a speaker grill and others?
In the plastic injection molding, again, it's usually for the venting applications and also conformal cooling, because there are some other materials which are adopted in plastic injection molding when it comes to cooling issues. They have a material
Hmm.
called Mold Max, which has a very high thermal coefficient, which helps with the cooling issues, but it's not as structurally as strong as 3D printed steel. So that's when we can print some areas which need that structural performance, which need that high mechanical strength, but at the same time, they have the cooling ability as well. So in injection molding, so far, what we're seeing in the industry and the projects and the customers we're working with is generally conformal cooling and venting, and a combination is more powerful to a lot of our customers.
Okay. Super cool. Like I said, I think a whole field of applications that we don't talk about enough in the industry. So I'm glad you got to talk about. Did you bring a injection molding tool sample as well?
Um, Not really, but I remember another thing that we have introduced in injection molding is the diamond finishes. So this is
Mm.
very interesting proprietary process that AarKel has developed again, where in the automotive lighting molding applications, especially when you're doing your lens cover and all your lighting plastic parts in the car, they need a very high finish. But you can't do it very well if you don't have a very high surface finish mold insert. So what we have done at AarKel is we've taken 3D printed material and we have
Hmm.
put it through some special process where now you're able to improve the density and improve the surface finish, and you're able to polish that surface to an SP1A1 diamond finish. I have a small sample over here which I can show you. And this is 3D printed. You can see it's 3D printed on as regular steel right out of the printer, but then on the
Hmm.
other side we've polished it to a diamond finish.
Wow,
So that's how you can. That's the
that is
surface
impressive.
finish you can achieve with 3D printed material, which is very unique. So now all of a sudden
You-
you're opening a separate segment of uh, tooling applications where you can introduce conformal cooling and you can create these unique finishes, which helps with achieving parts with the requirements that they need. So that's kind of a new innovation that we're working on. We're trying to push it to certain projects and get some successes over there.
Okay, so that really means that applications like automotive headlamps that have a very clear finish were not accessible via additively manufactured injection molding tools due to the um, natural surface roughness of an additively manufactured part. But through your proprietary process, you were able to achieve this diamond finish, which opens up a whole new set of applications that are actually very, very critical to the automotive industry. I remember if I when I was at BMW, in the pre-production, the headlamps were inspected very, very closely. Where do you see the parting lines? Where do you see the injection spots? They weren't allowed to be in certain areas, so it's a very particular visual inspection process around these applications.
Absolutely, absolutely. Yeah, they don't allow any blemishes, any defect. Um, it's very critical to get a very good part quality and a good surface finish. So we're excited about this new process, and we want to see what the new solutions we can provide to our customers, especially with the conformal cooling. And these days, you're seeing the cars evolve into much modern and unique designs where they're thin bezels and the lights are getting they're multifaceted, and you have two, three, four, five-piece headlamps in all these electric vehicles. So it's going to be more difficult to manufacture them with traditional approaches, and that's where 3D printing is going to help to achieve these unique creations.
Yeah, you know, they are pretty much the key to any automotive design. They're the eyes, so
Absolutely.
they gotta they gotta be they gotta be perfect. Now we talked a lot about the awesome innovation that you guys have been driving in the additive space, but typically those don't come without challenges. Like we said earlier, those don't come without mistakes. What are some of the key challenges you guys have approach. We talked about education initially. We talked about the magnetized hybrid inserts. Anything else that you can share that you stumbled upon? We're like, "Ooh, how do we solve that?"
Yeah, I mean, challenges are always there, and that's what keeps us from trying harder and being more innovative. Um, some of the big ones are cost. Cost is a big driver with 3D printing because whenever we interact with consumers, and their first comment is that the 3D printing technology is expensive compared to a traditional solution. So that's where AarKel is trying to make more headway in, whether it's faster parameter set or investing in multi-laser machines, or whether it is finding more competitive, cheaper raw material. And since this technology is getting more mature and mature over the years, you're able to see more steel players enter this market, and the overall cost of 3D printing is naturally coming down because there's more competition, more suppliers innovating, and the cost of the powder itself is going lower and lower. So we're trying to uh, introduce faster printing parameter sets and working with our suppliers for cheaper material, and also trying to invest in multi-laser machines. And that's kind of how the goal is to eventually bring 3D printing solution to our customers at the same cost of traditional solution. So that's eventually the goal. And
Mm.
it'd be interesting in the next 5 to 6, 7 years, maybe. But we'll see how the market develops. We're seeing the printers are getting bigger. We're seeing the materials getting cheaper, and the awareness, like you said, the education part of it. Sometimes we have challenges educating our own staff because it's a change. And, the designers need to think in terms of, hey, when I see a problem over here, when I see a customer pain point, I can use additive manufacturing as a powerful tool to provide a solution to our customer. So educating our existing staff, educating our customers, because many people come through our facilities and they don't even know what 3D printing is, and they didn't even realize that you could use 3D printing in metal. So these are all a lot of awareness issues, a lot of cost issues. So these are kind of some of the general challenges we're dealing with right now, and we're constantly trying to work towards them. Yeah.
Yeah. Yeah, naturally, cost is a challenge, and I'm guessing that your customers have to run that assessment of how much worth is a cycle time reduction, a lifetime increase of a die, or an injection molding tool, and does that offset the investment cost? Would you would you say that's in die casting or in injection molding that business case is easier for one over the other,
In our
or does it depend on parts?
It depends from customer to customer, but in our experience, we've seen that die casting has embraced additive manufacturing technology better. It's easy to integrate AM solution. With plastic, however, there are really some good customers who are willing to try out something unique and solve their issues. But at the same time, we get a lot of resistance from the plastic injection molders because they have tighter budgets. And,
Mm,
these are you're also working with an older workforce because a lot of skill trades is an older workforce, and the mentality shift for a newer technology is a challenge as well because they're always stuck in doing things the old way, and it's been working this way. So why do we have to change it? So convincing the older guys in the game also is a little bit of a challenge, I must say. But yeah, we're making headway everywhere.
yeah, yeah. Change is tough. Change is tough. Yeah, but I think you guys are doing a really awesome job. Also educating the industry. Um, Maybe talking about the next 5 to 7 year time frame that you did mention a few times now. Do you see additive manufacturing becoming more and more uh, dominant in the die casting and injection molding space? Do you see a certain limit where conventional manufactured tools are going to stay in a certain spot and additive manufacturing is going to be positioned in a different spot, or how do you see that evolve?
AarKel's vision is very crystal clear. Additive manufacturing is the way to go.
Mhm.
We're changing the way we do things. Uh, Additive manufacturing is not a choice for us. It's going to be a ready-made solution in all the tool builds we do. And we are using it very effectively. And some companies I have heard are investing massively on CNC automated cells and all sorts of different investments for making small components. But I think at AarKel we believe that investing in additives and the advantages is just so high because they're truly unmanned machines, and they can print over Christmas, they can print over the weekend, and that's the beauty of 3D printers. And you can print multiple small parts. You can fill the bed with 20, 30 parts at a time. Part consolidation and the productivity is so high with 3D printing. And we believe that's the way to go forward. And we'll know in 5 to 7 years how the market's changing. But we have a strong belief that companies which are not investing in 3D printing are going to be left behind.
Well, I think that's a really good sentence to end on. Yes, thank you so much for being on the show today. I learned a lot, not only about the die casting and injection molding processes, but also really what it takes to implement such a technology. I think you guys have done a really awesome job of embracing additive, not being afraid of trying things out, and I think the mistakes that you guys have made actually led to very interesting pieces of innovation, just such as the venting, the finishing technology that you guys have pioneered. So I'm really excited to see how you guys continue to drive the industry forward and be one of the key players there to show the way of innovation. So thanks again for being on the show.
Thanks for having me. Appreciate the opportunity.
All right. And thank you out there for listening in today. I do hope you enjoyed this conversation just as much as I did. If you did, please give us a thumbs up, leave us a review. And if you have any ideas or questions, feel free to also leave a comment in YouTube or just shoot us an email at additive.snack@eos-na.com. This was the Additive Snack podcast. I'm your host, Fabian Alefeld, and I will see you next time.